Okay, so now that we've established that there is missing mass from every atomic nuclei except for hydrogen, the simplest one, which is not connected to any neutrons, excuse me, we need to understand what happened to that missing mass. The mass has to be accounted for in some way. So although there really is no such thing as conservation of mass, there is something called conservation of energy. And it turns out that the missing mass was released from the nuclei in the form of energy. And Einstein's mass energy formula is what would allow us to calculate exactly how much energy left the nucleus as a result of this missing mass, this mass defect. The missing mass is actually referred to as the energy, in terms of energy, and is called the binding energy. And the binding energy is very simply the amount of energy that you need to put back into the nucleus so that the reaction can be reversed, meaning that we could separate all of the nucleons, all of the individual nuclear particles, the protons and neutrons, back into their individual parts instead of being combined together to produce that nucleus. Now we can calculate how much energy is in one atomic mass unit. If you remember in the previous problem, we ended up with a missing mass of about 1.67 U's, and that actually turns out to be more than the mass of a proton or a neutron. So let's calculate exactly how much energy 1 U is equal to. So using the formula, E is equal to mc squared, and in this case I want one atomic mass unit, and I would multiply that by the speed of light squared. Remember, one atomic mass unit is equal to approximately 1.6605 times 10 to the minus 27 kilograms times the speed of light, and the speed of light is approximately 2.9979 times 10 to the 8th, and then we need to square that. And so this produces an amount of energy equal to 1.4923946 times 10 to the minus 10th joules. Now this is a very small unit of mass, so what we would like to be able to understand is exactly how much does this in terms of electron volts. So let me remind you, so this is sort of an aside, that in terms of energy, let me say W, that work is equal to QV, and the electron volt is the charge on the electron times 1 volt. An electron volt is very simply the amount of energy that's required to remove an electron through a 1 volt potential, and this would then be equal to so 1 EV is equal to 1.6 times 10 to the minus 19 joules. Let's put a box around that. Okay. So with that in mind, we can make a conversion from joules into, for the electron or the unit mass, we can convert that to electron volts. So this is a pretty simple conversion. We're going to start with the 1.4923946316 times 10 to the minus 10th joules, and we know that 1.6 times 10 to the minus 19 joules is 1 EV. So then this produces a number equal to 9.315 times 10 to the 8th EVs. It's a capital V. Okay, so this is approximately 931.5 million electron volts, or 9.315 times 10 to the 8th electron volts. So we can establish this very simple relationship that one unit mass, one atomic mass unit, I should say, is equal to 931.5 MeV. M meaning mega or mega electron volts. So one unit mass is equal to 931 MeV. Now with that in mind, we can now establish how much energy is in a proton, a neutron, and also in the electron. So let's write down their mass. For the mass of the proton, the mass of the proton is approximately 1.007276 U's, and this is going to be equal to approximately 938.3 MeV. The mass of the neutron was 1.008665 U's, and that's approximately equal to 939.6 MeVs. The mass of the electron is equal to 0.000548 U, and that would be approximately equal to 0.511 MeV. So we have a new way of thinking about the energy that's missing from the atomic nuclei, and that is in terms of the number of MeVs that are missing. So the binding energy is again, very simply, it's the amount of energy that you need to completely separate the nucleus into its separate parts, into individual protons and individual neutrons. But there's another way to think about the binding energy, and that is that we would take the binding energy and then we would divide that number by the total number of nucleons in the nucleus, and then this would be called the binding energy per nucleon. The binding energy per nucleon is actually a very useful way of thinking about the binding energy in a nucleus, because the binding energy per nucleon is approximately the amount of work that you would need to put into that nucleus to remove one of the nucleons from the nucleus. And the reason why this is such a useful number is because the higher the binding energy per nucleon, the more stable that the atom tends to be. So those that are most stable, the most stable nuclei, tend to have a very high binding energy per nucleon, which is why they're bound together so tightly. If they have a relatively low binding energy per nucleon, then it's a little bit easier for us to separate those individuals. They're more likely to undergo a decay process. So with that said, let's take a look at one more example, and then we'll calculate some of these binding energy per nucleon, and we'll compare the relative stability of these atomic nuclei.